Okay, let's let's get back to work, quote unquote. But who's working here? Just me, right? I'm working. What are you doing? Sitting. That sounds accurate. What else? Paying tuition. Ouch. Paying your salary, buddy. True. Thank you. I'm trying to argue that with these bigger classes, I should get paid a lot more. It's been ineffective so far. Um,
200 professors?
what's that?
Wouldn't it 200 and 300 professors be cashing out then?
Yeah, I guess so. I'd be okay with that. I don't mind someone else making a lot of money too. Just talking about. You should never begrudge someone else. Just worry about yourself. So yeah, you're sitting, you're paying tuition. No, as we speak, I guess. What else are you doing? Yeah, I don't want to know actually. Who knows what you're doing back there, especially the back rows. Shout out to the back rows. What's going on in the back rows?
You just said you didn't want to know?
I don't want to know. But I want somebody to say, oh, yeah, I don't want to know. Okay, we don't want to know. So let's get going again. Yes, I'm recording all of that for who knows what reason. What we're going to do now is finish up our discussion of RAID. We'll do a few little simulations too of that. So what we saw is striping not really super great because performance is good. You just get the bandwidth. You kind of get to use all the disk, and you get parallelism, which is key from a performance standpoint. You get capacity, actually, which is really good. You get to use all the bytes, but you don't get reliability. When the more disks you have, the more likely it is for a failure to occur. And when a failure occurs, part of your address space is suddenly missing. Imagine how hard it would be to use memory if suddenly banks of memory disappeared, right? Part of your linked list disappeared. Same thing with a hard drive. When we lay down persistent data structures like files or whatever we're storing in our files, when we lay those down on a disk, if part of that disappeared, it'd be very hard to deal with. In fact, you'd have to start thinking about adding redundancy in your, in the file itself because you know that the RAID system isn't doing that. What we're hoping to do is to build a RAID system that transparently provides a more reliable disk array than just what we're doing with striping, than a single drive could be. So the first one we're going to do is RAID level 1, or mirroring. This is kind of a simplest one to understand. And then we'll do add parity, which is a little more complicated, but gets us some different properties that we might find interesting. Mirroring is pretty simple. We'll again have our disks here like this. And then we have that mapping problem again. But what we're going to do is for each logical block, we're going to keep 2 copies, 2 physical copies. So for each logical block, we're going to keep 2 physical copies. So maybe we'll do something like this. Block 0 we'll put here. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, etc. Okay. So that seems like a pretty simple idea. And again, these are the ideas that if you were given a bunch of hard drives and you said, hey, somebody said make these more reliable than a single hard drive, you would come up with mirroring. That's the easiest thing to come up with. You would say make a bunch of copies. And 2 copies is pretty good. But 2 copies, let's think about it. Well, let's think about a few different things. First, let's think about probably easiest thing to think about first is capacity. So we have n drives, and we each is size d bytes per drive. So our total capacity is, well, we have n times d bytes, but we have to divide it by the number of copies that we make of each logical block. Because as you can see here, if we're filling up, if we have just 2 copies, we're clearly getting half the bandwidth. I mean, half the capacity, sorry. I keep using the wrong words, which is important. So let's talk about reliability. Now here, let's think about what we can tolerate. And what we're basically saying, remember our fault model is that a whole drive can fail. Whole drive failure. So how many failures can we tolerate? Yeah.
So either one of the individual drive or up to in a special case. the corresponding drive. So you get 1 and 2 in its corresponding drive, but not the copy.
That's right. So if you didn't hear that, the answer was, and maybe it's apparent, basically the question is, how many disks can I eliminate and then still be able to access blocks 0 through whatever the max size of the disk array is? Clearly we can eliminate 1 because, or sorry, let's call this disk, this is disk 0 here, disk 1, disk 2, disk 3. Clearly we can eliminate disk 1 because all its contents are mirrored over here. And clearly we can eliminate one of these drives, 2 or 3 as well. So if we're lucky, what we can do is we can essentially tolerate n over 2 failures. But more likely what we're going to be is paranoid, and we're going to tolerate 1 failure. And then what we're going to do is replace that drive. So typical disk array, we're not like, hey, a drive failure happened, great, we have many more to go. Because if you're unlucky, what will happen is your next failure will happen to the other drive that is in the kind of the corresponding pair as we've arranged it here in mirrors. So I'll think of it generally as 1, and then typically what an administrator or whoever's dealing with the system would do is then like replace the faulty drive with a working one, and then actually rebuild its contents, which is a process we won't talk too much about today, but you can imagine happens, copying from the good to the bad, and then kind of install it back in the array and get going. So that's how we'll think about reliability. The most interesting thing to think about, though, is performance. Let's think about, remember we were thinking about random and sequential. Let's think about random I/O first. It's a little bit easier to think about. And let's think about writes first, since they are a little bit easier to think about too. So when we do a write, let's say we write logical block 3, what do we have to do? How many physical IOs do we have to do? Yeah, 2, right? Not 2. There's not too many guesses there. You guess 0, 1, 2, or many, or something like that. I don't know, a lot. What we have to clearly do is update both of these disks. Last time we were thinking of random I/O bandwidth, we were thinking of the whole bandwidth of the system and like how long, how much bandwidth do we get in total. But before we do that, let's just think of latency. How long does a single logical write take compared to if we had just done to 2 disks, compared to if we had done it to just a single disk? So let's say somebody issues a write to 3, then in parallel we issue the low-level physical writes. How long is that going to take compared to just doing a write to one of those drives? Maybe answers are it's faster because it's a RAID. Another answer is the same because they're in parallel. And another, it's longer for some other reason. And there may be a 4th answer, but I'm not able to figure out what it is in a different dimension. So what's the answer? What's the answer? Is it, when I'm writing to 2 drives, is it tends to be slower, the same, or faster than writing to 1 drive? Who thinks it's the same? Okay, who thinks it's faster? Okay, not a lot of support. Who thinks it's slower? Okay, why is it slower? Any intuition? It's about the same, but a little slower is kind of the way I think of it. Why is that? Why would it be a little slower? Yeah. Yeah, that's right. And why that might be slower to write, so that's a great summary. It's going to be as fast as the slowest of the 2 writes. Why might it be slower to write to 1 drive than the other? What might make them, one request take longer on 1 drive than it takes on another drive? Well, that's exact. No, same speed drives. I think your first answer is more onto it. Maybe you'll say the same thing, yeah? Yeah, exactly right. It might have been that we just did like a really long read over here on this drive to seek very far away from 3, and we might be very close to 3 on this drive. What did you can't see? You just can't see what I was writing? Yeah, it's over here. I didn't do a good job is what you're saying. Okay, here's where you should look. I don't even know what that means. So, so we could be far away on one drive. We could be close to block 3 on another because they maybe have done independent reads before then. Therefore, the write's going to take the max of those two, and the seeks might be a little bit longer. So when we think about it from a latency perspective, just latency, writes may be a little bit longer. I don't know what the universal math symbol for that is. So a little longer than, say, writes to 2 drives, a little longer than write to 1 drive. Now reads, let's think about reads a little bit. When we're issuing a read, let's say a read comes in and it's for block 2. Somebody says, I want to read block 2. How many physical IOs does the RAID have to do? Does it do 1 or 2? Some say 1, some say 2. Anybody for any other numbers? 3. It's a persistent drive. No, it's going to do 1 or 2. Generally, it does 1. What are we assuming then when it does 1? Sorry? Trust the data, exactly. You trust that either one is correct, which goes back to our fault model. Remember, our fault model was the drive is either working or not. So if it's working, we can just read from it, and we trust if we get one copy, it's the same as getting the other. So we don't read both. We just read one, and we trust that's going to happen. So a read, if you think about writes go to 2 disks, but reads just go to 1. If we didn't trust the disks at all, what we might do is we might have like 3 copies of every piece of data on 3 different drives, read from all of them when we want to read, and then basically vote. If any 2 of them agree, that's a majority, and that's probably the right data. Of course, if they're really malicious, they won't agree at all, and you can't do anything about it. But that's certainly some old RAID arrays did that, but in a modern mirrored RAID array, you would just read from one of the underlying drives. Now I'm belaboring this, but for a reason, because I want us to be able to talk about random I/O bandwidth. Random I/O bandwidth means when I'm issuing a lot of random I/Os to the hard drives, to all, to block 0 and 100 and 1,000 and whatever, 9,000 all at once, how much total bandwidth am I getting out of the system? Well, remember a single disk gets R megabytes per second of random I/O. Remember that might be like 1 megabyte per second, so it's pretty slow. So when I'm reading from n disks, how much bandwidth do I expect in a mirrored array? Well, we have n disks, and we can use them all. So we're hoping it's n times r. Now in terms of writes, the latency of a single write was about the same to 2 disks as it was to 1, though we argued it was a little slower. What's the bandwidth that we get out of this disk system when we issue a huge number of writes to it? Is it the same bandwidth? Is it n times r, or is it something different? What do people think? What do people think? N times r or some other algebraic twist of fate? Yes.
N over 2 times.
Yeah, I like it. N over 2 times r. N over 2 times r, because we have to pay for this cost. So let's see, I have a little simulation that shows this, just in case. Let me see if I can get this thing going. I wrote it down here somewhere. So these are random reads to a mirrored system. Let's see if this works. Oh no, I have to remember. What do I have to remember? The magic magnifying key sequence. Oh, well, you know what? You can kind of see it without, you don't need to know the numbers here. We'll do magnification later. So what this is showing is kind of 4 drives, more or less. Actually, exactly, not more or less. 4 drives exactly. And then it's, instead of showing all the seeking and rotating, it's just kind of showing like a pretend where the disk head is right now. So they kind of all start at block 0. And then up here we have a bunch of requests which we're going to read. Like if you can't see, it says read 36, and then 25, and then 22, and then 7. And we're going to issue as many of them as possible at once so we can try to keep all the drives busy. And what you see down here are at the bottom, like when reads are happening, you see orange, and when writes are happening, you see yellow, and there's like little counters how many reads and writes occurred. So when we're doing a lot of reads at once, what you see is the requests are going all over the place, and the drives are each servicing them in parallel. And you can imagine why that would be 4 times faster than having a single drive doing it. Because if a single drive did it, it would just be one of those drives doing all those requests. So, and that you can see, if you can read in the very top, in this very tiny text, it says about 576, about 600 time units to complete all those reads. Okay? So any questions about how that works? Does that make sense why we get that bandwidth that we were talking about when we were looking at this? We said n times r, because the more disks we have, the more random bandwidth we can get. Okay, so let's kill that. And then let's look at the same thing, but let's look at random writes. So essentially the same workload, but now we're writing each logical block that comes in, right? So each logical write has to turn into 2 physical writes. So when we start this, you can already kind of see we're doing more work for every write. We're writing to every pair instead of every one. Because there are no reads mixed into this workload, the writes kind of happen at the exact same time. So this effect of one write being slightly slower wouldn't happen because we never throw a read in there to kind of move one of the drive heads off of where it is. And you can see that it's going to take longer than the reads. And in fact, it takes about twice as long, about 1,200 time units instead of about 600, which is showing that our bandwidth is about half. And that should appeal to our intuition. It's, even though the latency of a single write is about the same as to 2 disks is about the same as it is to 1 disk, there's no magic when it comes to bandwidth. We get half the bandwidth total. Any questions about that? Make sense? Okay, so let's think about a slightly trickier case. So now we're talking about sequential reads and writes, or large reads and writes. So now we're going to talk about reads down here and writes here. Writes are kind of an easy case. Again, a single disk gives s megabytes per second, which we might think of as maybe 100 megabytes per second, something like that. And again, because we're writing here, you might say, well, how much bandwidth do you get when you're reading or writing from these drives sequentially? What do we think? How much bandwidth do we get? What are some different answers? Some different possible answers are, well, we're writing to it sequentially, so we're going to, in fact, let's think about how we do the writing. So remember our mirrored array looks something like this. I'm going to just replicate that down here for make this diagram a little simpler. So when we're writing, we're going to be issuing writes to 0, 0. Let's say we're sequentially writing the first so many blocks, 0, 0, 1, 1. Then we're writing 2, 2, 3, 3. Then we're writing 4, 4, 5, 5. And then we're writing, we're issuing all these writes at once. We're giving a lot of writes to the drive. So how much bandwidth are we going to see from the user's perspective? We're using all n of the drives. There's n drives. But how much bandwidth does it feel like to the client? Yeah, n over 2 times s megabytes per second. And it feels that way because you can kind of intuitively appeal to that if you just wrote to this drive and this drive and you didn't have those other mirrored pairs, you get that same bandwidth, right? You're just writing those blocks out and it takes exactly the same amount of time. A little trickier are reads. What are we going to get from reads? Yeah. Love it. This is actually an answer, not a question. I'm going to turn it around on you.
If you wanted to emphasize performance for writes, would you do writing to begin with and then later on just not active copy over for dependency?
That's a really good question. So the question, if you couldn't hear it in the back, was, hey, it seems like what we could do is basically if we want the max performance on writing, where we're paying a cost for writing in mirrored systems. So what we could do at first is just write to all, like in striping mode, somewhere on the hard drives, get full bandwidth, and then later in the background, kind of make some copies when nobody cares, and therefore maybe get some sort of higher total performance out of the system. That's actually called a redundancy level hierarchy, and that was introduced as an idea in 1995. So that's pretty good. You're actually within not so far of the cutting edge. But that was actually an award-winning paper. It's called Auto RAID. It came out of HP Labs and was a very excellent idea. So congratulations on having a very good idea. Just a little bit late for getting like a paper out of it. But that's pretty good, yeah. Good job. Who knew that you would get applauded? So that happens, right? When you're thinking about systems, you might have ideas, and often you can tell how close you're getting to having a new idea is like by how many years, how many years back you are, right? So if you're 20 years back, then you have your next idea is only 10 years back. Eventually you start getting very close to current time, and eventually you break through that and have an idea somebody hasn't had before. And that's how progress is made in the research world. So good, keep doing it. So that's a great idea. We're not going to talk about something quite as sophisticated as that, but you certainly could do that. And you have a little bit of risk you're willing to play there, right? The risk you're willing to do there is I'm writing in striping mode at first to get bandwidth, but if I lose a disk at that point, I lose the data. But maybe that's okay for 5 minutes. And there are many other places in this storage system where I'm willing to do that, as we'll talk about in the future. That's it. And then there's other places you can do it too. We'll see in a second when we introduce RAID 4.5. So great idea. Going back to my question and your answer, what's the bandwidth we're getting out of reads? When we're sequentially reading from these drives, well, how are we going to do it? Maybe we'll, let me do this in a different color. So maybe we issue reads. Let's say we issue a bunch of reads. We're reading, oh, sorry, not like that. We don't need to read both, right? So let's say we read 0 from here, and 2 from here, and 1 from here, and 3 from here, and 4, and 6, and 5, and 7, etc. So when we're reading, we're using all the drives. What bandwidth are we going to get if we read in this pattern? In blue. What bandwidth are we going to get when we're reading 0, 4, 8 from this drive, 2, 6, 10 from this drive, 1, 5, 9, 3, 7, 11, yeah. Sorry? So one guess is n times s. Is this going to achieve n times s? N times not quite s is another guess. Approximately s? That's another guess, yeah. 2 times s. Well, okay, well, that's another guess. It's another guess. Why do I keep asking for more guesses? Can anyone guess why I'm asking for guesses? Yes. N over 2 times s. That's right. It is n over 2 times s. Sometimes that bothers people, and that's what we're here to do in this style of education. It's bother-driven education. It's quite the rage. You bother people, and then they pay more attention. So why does a drive, what bandwidth do we get out of a drive when we're skipping every other block? Think about what's happening. The disk is rotating, right? So disk rotating, it doesn't go faster if you don't read every block. You still have to wait for that block to rotate under the head. So reading 0246 takes, or 02468 takes the same time as reading 0, 4, and 8 because the disk is rotating under there. You can't skip ahead on that rotation. It rotates at a fixed speed, which means when you're reading every other block from a particular hard drive, you're getting s over 2 megabytes per second. And if we think about how many drives we have n drives. So it's really n times s over 2 is a way to think of it, or n times s over 2. Now, you can do a little better than this if you're clever. What could you do? Yeah. Yeah, what we could do is if we know we have a huge chunk that we need to read, we could kind of read the first chunk from here, the second chunk from here, a third chunk from here, and a fourth chunk from here. So in that case, if you're kind of willing to pay a little bit of a seat cost on some of the drives, you can actually get a full bandwidth of the drives, which goes back to your original answer of n times s. But for simplicity, we'll just view it as n over 2 times s. So that's a good point. Okay, so let's look at mirroring. Mirroring looks, actually, it's interesting. Mirroring has terrible capacity, right? You're giving away a lot of the drive capacity. You bought a terabyte of drives, but you only get half a terabyte. Or you bought 10 terabytes, you only get 5 terabytes. You're giving away a ton of capacity. You get pretty good reliability, but in the end, we're really just wanting to tolerate one disk failure and then be able to replace it with that small window of vulnerability that occurs between the time of failure and the time of replacement. The issue that we have with performance is writes are expensive. Reads, actually random reads are really good. Random writes, you pay a bit of a cost, n over 2. And then sequential I/O, you pay a cost. Unless you're very careful, you pay n over 2 in all cases. It turns out this performance cost is actually pretty good, especially in random writes. We'll see cases where it's worse in a second. So what we want to do is develop something that maybe gets us better capacity than a mirrored system, and then better, but maybe going to have different performance characteristics. Okay, and so that's why people invented the next kind of RAID. So we'll talk about these parity-based RAIDs. And that's RAIDs level 4 and 5. So first we'll talk about RAID level 4. Okay, so I guess why don't we just describe RAID level 4, then we'll take another breather at that point. So RAID level 4 is based on this idea of parity, which we're going to use our old friend the XOR function in order to deal with. And the way we're going to have that is we're going to have some number of data disks, and then a parity disk, which is going to encode some information about the data disks, such that we can, with a single failure, figure out what the data must have been on the failed disk. That's our goal with this parity disk. So let's say we have 3 data disks and then 1 parity disk for simplicity, simple 4-disk array. And what we're going to do is put some, so we're going to put some data here, some data here, some data here, and then our redundant information is going to be limited to just, say, this 1 disk. The way we're going to encode this information, I'm going to just pretend this is really like a block of data, but I'm going to pretend it's just a bit for simplicity. Okay, so I'm going to pretend it's a bit because it makes the little mathematical things I'm going to do easier, but this is really being done over every block instead of every bit, and I'll talk about that more in a second. So let's say we have some data like this. All we're going to do over here in the parity disk is basically make sure we're trying to maintain a certain invariant, and that's for each row. So this is a row of data. For each row, what we want to make sure is there are an even number of ones. Okay, we'll call this even parity. So in this case, we have 1, 0, 0. There's 1, 1, 1 out of 3. And to make the whole row have an even number, or in this case 2, we're going to put a 1 here. Okay, so this is a very simple idea. So if we have 1, 0, 1 over here, we would put a 0 over here. If we have 1, 1, 1, we put a 1. If we have 0, 0, 0, etc., we put a 0 over here. Now, like I said, disk arrays are not, we're not doing this at a bit level. We're going to do it at a block level. So really, this would be a block, and this would be a block of data, let's say 4K or something like that. And this would be a block, and this would be a parity block. And all that means is that there's a bitwise, we're doing this at a bit level. So if this were 0, 0, 0, this would be 0. And if the next bit were 1, then 0, then 0, then we'd make the parity 1 over here, etc. I'm just going to think about it at this level because it's just, again, like I said, it's easier to think about. Does that make sense? Any questions about that? Okay, so now we have to see what this parity system does for us. Hopefully what you can kind of observe here is, let's say a particular drive got lost. what you can see from here is, well, how do we compute what's on this drive? How do we recover this data? What do we do? One is we call somebody. Can you help me? My hard drive has failed. I've heard that it has a RAID on it, and I didn't pay attention in that lecture in class. That's one option, yes. A better option. Well, I think that was close. The invariant is the right thing to look at. The invariant, remember, tells us exactly what we need to know, which is we know when we created this row of data, we know that there were an even number of ones. So when we're computing what's missing, what do we look at? We look at how many ones are in the data and the parity. And if it's an odd number, which you can see here it is, there's 1, 1, then we know this must be a 1. When it's an even number, 0, then we know this must be a 0. When it's, again, an even number here, 2 ones, we know this must be a 0 as well. In fact, it's the exact same calculation we did to compute the parity, right? It's just, are there an even number of ones, and how do we make each row have an even number of ones? That's all this is doing. And in fact, it turns out that XOR does exactly that. So if you compute the XOR of all these bits, it gives you this. And similarly, if you compute the XOR of any n-1 bits, it gives you what the other bit should be. And you can figure that out on your own. So that's the basic idea. Now we have to turn this into a reading and writing, this array. So let's talk about reading and writing. So this is kind of getting towards our, let me do this, actually. Let me do one thing before then. So first question, does the basic process make sense? We have each block, it's like we're doing striping, right? In fact, what does this look like? It looks like a striped array, right? It just looks like it's striped over one less disk, and that we've added this parity disk on the side to allow us to recover from errors in our striping array, right? That's all it looks like, it's striping plus a parity. And so we have a bunch of blocks we've striped across these drives, and then we have this parity array. Now this, so let's think of it like this. So we put block 0, 1, 2 here, 3, 4, 5 here, 6, 7, 8 here, and then parity 0, parity 1, parity 2 here, etc. Now actually at the break there was a good question asked, which I forgot to answer, which was, why do we stripe like this across these drives instead of kind of striping downward? Like why not 0, 1, 2, etc., and then, whatever big number x plus 1, x plus 2, whatever the next big jump is, y, and this would, of course, end at x minus 1, and this would end at y minus 1, and this would be, whatever the max size is, y plus 1. Why don't we stripe, why not this? Why do we stripe this way? Why do we stripe horizontally? Yeah.
Because the data is usually in sequential. So unless the data you read is like from 0 to y, otherwise you're going to only read from 1 to 2 bits, which is less efficient.
Yeah, that's exactly right. So striping like this means that if we have requests for a consecutive number of blocks, like from 0 to 100, that we get to utilize all the drives. It allows us to have parallelism, right? So really the reason is parallelism. If we stripe like this, then what we get is when we read from 0 to 100, we're just using one drive, and that means we're not going to get full bandwidth out of the system. So that's generally why. In any case, this is what our parity-based RAID system looks like, and in fact, this is called RAID 4 because it just has a single parity disk. And what we have here is we have to start understanding things about this. So let me erase this down here. And let's start evaluating this a little bit. Easy kind of things to evaluate. Reliability. How many disk failures can we tolerate? Well, we can tolerate one failure. We know if one thing goes away, we can reconstruct it. If two things go away, well, we don't know. We can't. Then we don't have enough information to know if there should have been an even or odd number because it could have been 0, 0, 0, 1, 1, 0, or 1, 1, and therefore we don't know. We don't have enough information. We can tolerate one failure. Capacity here is good, right? It's n minus 1 in this case times d, say, megabytes of space or gigabytes or whatever. And so, compared to our mirrored system, this is much better capacity, right? It has similar failure characteristics in that really we can tolerate one failure in either system, even though you could get lucky in the mirrored one, but it has much better capacity property. The interesting case, and this is what actually, let's just do a quick analysis of this and then take another break, is the performance. How do we understand performance of a RAID 4? So let's think about that just quickly. Let's say we're doing random reads. So random reads mean we might be reading blocks 4 and 6 and whatever, 11 concurrently. So we're issuing a lot of reads to the drives and we're reading them all concurrently. And so if the random bandwidth of a single disk is r megabytes per second, what do we expect to get when we have an n disk array, which includes parity? Parity is one of those disks. What do we expect? Yeah. N minus 1 times r. Now let's do sequential reads. This is random bandwidth. Sequential bandwidth of a single disk is s megabytes per second. When we're reading from a RAID 4 disk array, well, we can sequentially read from all of these in parallel. Notice we're not using the parity drive, so that's okay. But we're going to get pretty good bandwidth. We're going to get n minus 1 times s. Sequential writes turn out to be a good case too. If you have large writes going to a RAID 4, what you have to do is, let's say you get writes to block 0, 1, 2, 2. So the OS above you, by the way, we haven't talked at all, another good question asked at the break, we haven't talked at all about, well, how do we decide which blocks to read on a disk or in a RAID? Well, the file system is going to map files and directories and all those things that you use already today down to these blocks. We're going to learn about file systems and how that mapping occurs later. But for now, we're just assuming that somebody's reading or writing these blocks. We don't know how it happens. So if we get a big write, let's say to 0, 1, and 2, what are we going to do? The RAID array is going to receive block 0, 1, or 2. It's then going to calculate what the parity is, parity 0. In fact, it's going to do that probably through specialized hardware in a RAID array. So it's going to do that very quickly. In fact, we're going to view it as something that doesn't take any time. So we're going to immediately, when we have a bunch of data, 0, 1, and 2, we're going to immediately, very quickly compute the parity, and then we're going to be able to write them all in parallel. So we're going to be able to write the data and the parity in parallel. So that means we're going to be utilizing all the disks, but to the user, it doesn't matter that you're writing to parity. It just feels like you're getting, and I keep wanting to write r there, you want to get n minus 1 times s, because it's essentially the same as if you pretend you did not even have, let's say we didn't even have this parity disk. It's just like writing to a striping array of n minus 1 in size. So it's the same thing. Now what I'll do is, because nothing is better than a cliffhanger at the break, the question for you to figure out without looking it up, for example, in the book, because that would be lame, is what's the random write bandwidth that we get when we're using a RAID 4 array? In fact, the thing you have to think about is when we write, let's say we have a write that's targeted to block 4 right here. Let's say we want to write to block 4. What do we have to do in order to update the row so that our invariant is maintained? And on that dramatic cliffhanger, we will go to the next break. All right.